Hi, welcome back. Welcome to Unacademy. Unacademy is the India's largest online learning platform. I'm welcoming you all to this platform. About myself, I G Venkata. I have total 16 plus years of teaching experience, and so far I mentored more than 60,000 plus students for their GATE examination. Okay, and at present I am pursuing PhD from JNTU Kakinada, and my specialization is in VLSI. Now, see if this app, Unacademy learning app, is in your device, it's okay. Otherwise, we check how to get this app. See, just to open your Play Store, in that type Unacademy. After that, you get the app like this. Now, click on install button. Once you click on this install button, it will install the Unacademy learning app into your device. And once you open the device, you get what are the different courses available in Unacademy, and each course handled by who are the top educators. Okay, you get that information. Here we check few of the top educators. See, Tiwari sir, he is the topper in IIT, and Ankit Goyal sir, he is the GATE electrical 2 times all India first rank, and Jaspal Singh sir, he is the ex-IAS officer, and Jain sir, he is having a plenty of experience in computer science. Here are the top educators, and a few more top educators here for different departments. Now, I am happy to announce that recently we started 2 batches for electronics, electrical, mechanical, civil, and 1 batch for chemical engineering. Okay, in these 2 batches, 1 batch is for GATE 2022 and another one is for GATE 2023. So there is a Ascent batch for GATE 2023. This is for electrical department, and here are the top educators who are going to handling the subjects for this batch. Okay, this batch was started from 1st of February 2021. Okay, so don't waste your time. Now, during subscription, don't forget to use my code VRAW10. Okay, and next I'm going to the same Ascent batch. This is now for electronics and communication engineering. Here are the top educators who are handling the subjects in this. Okay, and again, Aval batch. This is for GATE 22, and for electrical department, here are the top educators who are handling the classes in that. And this batch also, all the batches are started from 1st of February. And next Aval batch for GATE 2022, this is for electronics and communication engineering. Here are the top faculty who are handling the classes in this. And next there is a Aval batch for GATE 2022. For this time, this is civil engineering. Here are the top faculty who are handling the civil engineering subjects. So Jaspal Singh sir, just before we verified, is the ex-IAS officer. Next, Ascent batch. This is again for civil engineering, and it was for GATE 2023. And now this batch was started from 25th of January 2021. Now, chemical engineering. So this is the first batch of the chemical engineering. Here are the few of the top educators from chemical engineering department. Now you must thank to Unacademy to provide a faculty of different disciplines, of a very good faculty. Okay, they are collecting from throughout the India. Who are the good faculty? They are collecting all those, and they are providing a benefit to the students. And one more thing, it is very difficult to get the chemical engineering faculty at outside. Okay, for GATE examination especially. So here they are providing that facility to you. Okay, if any one of your friends are in chemical engineering, please suggest them without wasting your time, their time, join in this. Okay, this batch was also started from 25th of January. And again, Aval batch, this time it is for mechanical engineering. Here are the top faculty working on mechanical engineering. This batch also started from 25th of January. And don't forget to use my code during subscription VRAW10 by using my code you get 10% discount. And next, there is a ascent batch for mechanical. This is for GATE 2023. Okay, here are the top faculty who are handling this subject in this batch, and this batch also started from 25th of January. And don't forget to use my code VROUT10 during subscription to get 10% discount. Now, just once again we check what are the different disciplines available in an academy. So mechanical engineering there, electrical, civil, production and industrial, instrumentation, computer science and IT department, electronics and communication engineering, and chemical engineering. These are the different engineering disciplines available for GATE and engineering service. Now, in an academy, there are two types of subscriptions. One is plus subscription. Plus subscription is the basic plan. Second one is iconic subscription. Iconic subscription is the next level of the basic plan. So in this you get the personal coach. For every student there is a personal coach. Okay, now the common to both is your classes are going to be handled by India's best educators, and there are interactive live classes, structured courses and PDFs they provide to you, and live tests and quizzes. Now here it is going to be the important point. So in this iconic, okay, we are assigning a personal coach to you. Now the job of this personal coach is whatever the test you written, whatever the examination you attempted here, that paper is going to be analyzed properly. Okay, and where you are strong and where you need more preparation, and where you are doing the mistakes in the examination. Okay, how to get a more score in the examination, everything they will prepare and they will provide that to you in a proper study planner point of view. By following this proper study planner, at the same time they provide study material to you. Okay, by following these two, definitely you get success in your competitive examinations, no doubt at all, because all these things are prepared by India's top educators. Already they got success in their career. Okay, already they came from that level. They know what are the heights and downs, ups and downs in that case. Okay, already they overcome all those things. Their experience, they use their experience to you. Okay, so don't waste your time and join immediately. Now if you check the amount point of view, for 1 month subscription in plus plan 5,500, for 3 months this much, and 6 months and 1 year 30,250. Okay, and there is 18 months plan also is there. It is 38,500, and 24 months it is 44,000. Now don't forget to use my code during subscription VROUT10. By using this code during subscription VROUT10, you get 10% discount. For example, if you check the for 12 month subscription, it is originally it is a 30,250. With by using my code you get 10% discount. After 10% discount it became 27,225. If you compare this amount with the expenditure, travel expenditure, what you are spending throughout the year to attend GATE classes somewhere outside, just it is more than that. Hardly 3 to 4,000 variation for that one and this one, not more than. Okay, this is the basic plan. Okay, now if you take the iconic plan, in iconic plan we have two subscriptions, 12-month subscription and a 24-month subscription. 12-month subscription and 24-month subscription. Okay, for 12-month subscription, after getting 10% discount, after 10% discount it became 45,225. 45,225. Okay, now for 2 months, that means 2 years, it is 74,000. Don't waste your time, enroll today itself, because whatever thing is happened, your learning process not be stopped, it should continue. Okay, and we don't know at what time what will happen. Okay, so at present we are in pandemic. It is very difficult to going outside and doing some work freely. We are moving outside, but with some tension. Okay, so without wasting your time, okay, without moving anywhere from your home, just by sitting at your home itself, you can get all the benefits. More than that benefits, what you are moving, where you are going to join somewhere and getting classes, okay, you can get that classes by sitting at your home itself. Guidelines, examinations, everything you get from here, from your home itself. From an academy you get everything. I think so for a student, not more than that required. They will provide plenty of information to you, plenty of data to you. Number of faculty are there. Okay, all are top faculty, all are well experienced faculty. Okay, so don't waste your time and don't forget to use my code VRAU10 during subscription. Okay, now this session we are going to solving the some problems on semiconductors. Okay, see this problem. An intrinsic germanium sample at room temperature has resistivity 50 ohm to centimeter. Intrinsic germanium samples are it is, that means intrinsic resistivity rho I equals to, we know that 1 by sigma I. So we know the equation for it. So they given it as 50 ohm to centimeter. Okay, from this what can I get? So we know the equation for this. 1 by sigma I is n into ni into q into mu n plus mu p. That is the equation. Okay, just leave it. Now the sample is uniformly doped to the extent of 10 power 16 to 10 power 13 arsenic atoms per centimeter cube and 10 power 14 boron atoms per centimeter cube. So arsenic is Nd, that means they given Nd. They given Nd value. Nd is 6 into 10 power 13 per centimeter cube. And arsenide and boron atoms 10 power 14, that means Na is 10 power 14 per centimeter cube. Find the conduction current density if an electric field of 4 volt per centimeter, 4 volt per centimeter is applied across the sample. So here they are taking the semiconducting bar. Okay, initially it is an intrinsic semiconductor. When it was at intrinsic, it given this much resistance, this much resistivity. Okay, now it is subjected to some electric field. They are applying some electric field. Okay, so once electric field, it became positive, let us take. Okay, it became negative. Now electric field is directed away from positive towards negative. Now the amount of electric field what they applied is 4 volt per centimeter. That much electric field they are applying. Now at the same time it was doped with Nd and Na. Okay, now in this case what is the current density? So we have two types of current densities: drift current density and diffusion current density. Drift current density is by the application of electric field, and diffusion current density is due to the concentration gradient in a semiconductor. Concentration gradient in the sense change in carrier concentration with respect to distance. Okay, now here, so this is current density. We need drift current density anyway. Finally, drift current density, J drift I want. Okay, we have an equation for drift current density. Carrier concentration into, so here it is doped by Na and Nd both. In this two, if you observe, Na is more, so Na is greater than Nd. Once Na is greater than Nd, it behaves like a From this, I am concluding that this material, this semiconductor behaves like a p-type semiconductor because Na is more. So once it is p-type, the drift current density of p-type semiconductor is under steady state hole carrier concentration into Q into mu p into applied electric field. That is the equation for drift current density. Okay, and here they given mu p mu n, they given both the parameters. So we know we get the value, we know the value of mu p already they given, and we know q, and they given electric field also. Now you need to get the steady state hole concentration. Okay, see, the hole concentration is, it is a compensated doping semiconductor. Compensated doped semiconductor. Okay, because it is not doped with a single type of impurity. It is doped with two different type of impurities, Na and Nd. Okay, and that too Na is more. Now, if you compare this, so Na can be written as, you can write Na is 10 times 10 power 13. So it is 10 power 13, 10 power 13. It is 10, it is 6. So more or less equal, approximate, not much variation. Na is not much greater than Nd. Okay, then at that time you can write, we have a standard, we derived already this equation in previous classes. Now concentration of holes is Na minus Nd by 2 plus square root of Na minus Nd by 2 whole square plus Ni square plus Ni square. Okay, now, so I know the value of Na and Nd. First I am going to that. So Na minus Nd is, it is a 10 into 10 power 13 minus 6 into 10 power 13. It is a 4 into 10 power 13 per centimeter cube. 4 into 10 power 13 per centimeter cube. Okay, now I don't know the value of Ni because in that problem they did not give an Ni, but they given a clue to you to calculate Ni from this. Now first I am calculating Ni from this. Now from this, Ni is 1 by, taking this 50 this side because it is 50 they given, 50 into Q is 1.6 into 10 power minus 19 into mu n plus mu p. It is a 3800 plus 1800. That is the mu n plus mu p. Now simplifying this, now it is 1 by, so it is 50 into 1.6. Okay, so it is 80. So it is 80 into, taking this 10 power 19 up, now at denominator, numerator, now it is 10 power 19 by, it is 56 into 10 square. Now this 10 square and this 0, now it is 3, it is 10 power 16. Okay, now it is 10 power 16 by 8 into 56. Now we can write that 100 by 8 into 56 into 10 power 14 per centimeter cube. Now I am going to simplify that. That is 100 divided by 8 divided by 56. It is 0.22. So it is 0.22 into 10 power 14 per centimeter cube. So now I am taking this is 2.2 into 10 power 14 per centimeter cube. That is the Ni value. So far we know the value of Ni also. Now Na minus Nd also we know that. Just substitute the values in that. Now P naught is Na minus Nd 4 into 10 power 13 by 2 plus square root of 4 into 10 power 13 by 2 whole square plus Ni square. Ni we got 2.2 into, see I am converting this one also in terms of 10 power 13. Now it became 22. So I am writing that directly. So it is 22 into 10 power 13 whole square. Now it is 2 into 10 power 13 plus square root of, see this is in this it became 2, 4 into 10 power 26 plus 22 square 484, 484 into 10 power 26. Now okay, now is 2 into 10 power 13 plus I am taking this 10 power 26 common from this. Now it became 10 power 13 by coming out of the square root into square root 484 plus 4, 488. Now square root of 488 is 22. So it is 2 into 10 power 13 plus 22 into 10 power 13. So it is 24 into 10 power 13 per centimeter cube. That is the whole concentration. Now once you know the whole concentration, just go and calculate the drift current density. Therefore J drift is P naught into Q into mu P into applied electric field. So P naught we got 24 into 10 power 13 into Q 1.6 into 10 power minus 19, and mu P they given 1800, and E they given also 4 volt per centimeter they given. Just as substituted values into that, not more than that. Okay. Now simplify this. So it is 10 power 13, 14, 15. Now 10 power minus 19. Now it is 10 power minus 4. Okay. So 24 into 1.6 into 4. 24 into 1.6 into 4. That is 153.6. 153.6 into 10 power minus 4. So this is a 15.36 milliamps per centimeter square. Amps per centimeter square, milli. That is the drift current density provided by that semiconductor. Sir, in this problem, initially they given the intrinsic germanium resistivity. From that we calculated the Ni value of that germanium, because they did not given initially Ni value. But so far what are the problems we solved? In most of the cases they provide the Ni value of the silicon or germanium. Okay. And after that your material is doped compensated doping, compound doping. Okay. In that they added both Na and Nd. From this Na and Nd we compare that those two. After comparison, Na is greater than Nd. So it means your semiconductor after doping of Na and Nd, it behaves like a p-type semiconductor. And now once it is a p-type semiconductor, its whole concentration is approximately Na minus Nd in general case. In this sense, if the net doping Na minus Nd is much greater than Ni value. Okay, see, this is we got 2.2 into 10 power 14, and Na minus Nd is you got 4 into 10 power 13. So not much greater. Okay, so I am going to a standard equation. So this is the equation I use it to calculate the P naught. Already we derived this equation also in previous classes. So it is Na minus Nd by 2 plus square root of Na minus Nd by 2 whole square plus Ni square. Just I substituted whatever the values we have in that. After substitution of values, I got the P naught value. So once we know the P naught value, that means under steady state hole concentration in that semiconductor after doping. Okay, once you know the P naught and Ni already we calculated, just I taken these two values and substituted in drift current density equation. Finally, I got current density of the order of milliamps per centimeter square. Okay, so this is the problem. Okay, so practice problems. How many number of problems you solved, you became that much strong in your subject. Next one is, see, the resistivity rho naught of germanium sample is measured at 300 Kelvin. Okay, they have a germanium sample. They measured the resistivity rho naught at 300 Kelvin. Fine, good. The sample is then remelted and doped with 4 into 4.4 into 10 power 16 arsenic atoms per centimeter cube. See, the sample is then remelted. It is melted and doped with arsenic atoms. Melted plus doped with arsenic atoms. The new crystal has a resistivity of 0.1 ohm to centimeters. See, after remelting and doping, number of carrier concentrations are vary in that. Okay, after doing this thing, it became an n-type semiconductor with resistivity of 0.1 ohm to centimeter. Okay, now determine the type and concentration of impurity atoms in the original sample and value of rho naught. Assume mu n equals to 2 mu p equals to 3000. So you need to identify initially whatever the semiconductor they taken. This is initially which type of semiconductor? That is the meaning of type of semiconductor. Type. Is it n type or p type? And initially you mentioned resistivity is rho naught. So its resistivity you need to mention, you need to calculate. At the same time, whatever the concentration of impurity atoms in the original sample, in this case, what is the carrier concentration in this, or impurity concentration in that? Majority carrier or impurity concentration, more or less both are same. Okay, how many there are, you need to measure those things. So first I know this one, I start from this point because clearly they given it is a n type and its resistivity is 0.1 ohm to centimeter. Okay, now after doping they given resistivity of n type is rho n, which is 1 by sigma n. They given it as 0.1 ohm to centimeter. Now it is nothing but a 1 by, for n type, so electron concentration into under steady state Q into mu n. So this is 0.1 ohm to centimeter. So they given Q value and mu n value to you. Just I am substituting that. Now from this I get n naught equals to 1 by 0.1 into 1.6 into 10 power minus 19 into mu n. Mu n is 3000. Okay, now it is simplifying this one, this one. So it is this one and it became a 16. Okay, now this one and it is 18 minus. So it is 10 power 18 by 10 power 18 by 16 into 3, 48. Now its value. So it is divided by 48. It is a 2.08 into 10 power 16 per centimeter cube. So approximate value I am taking, it's not a problem. Now 2 into 10 power 16 per centimeter cube, because for easy calculation purpose, that is the n naught value. Okay, see, compared to n naught, they given nd value, given nd. So whatever the doping they done is given nd equals to 4.4 into 10 power 16 per centimeter cube. Okay, see, compared to doping, number of charge carriers in that n-type semiconductor is less. Compared to the amount of doping what you done, number of charge carriers in that is less. Okay, that means electron concentration is decreased compared to doping. Okay, if it is initially a n-type semiconductor, once you are adding nd, now carrier concentration has to be more than nd. But carrier concentration after doping is less than the, sorry, after remelt and doping with that, carrier concentration is less than the doping. Okay, that means initially it is a p-type semiconductor. Okay, and that was doped with nd. After doping that with nd, it became n-type semiconductor of this much carriers. Okay, that means now, so after doping it became n-type semiconductor. Its carrier concentration is n naught. Now we can write that n naught is nothing but a nd minus na, because it is a compensate doping. Okay, nd minus na. So we need to calculate initially which type of semiconductor. So here it is na, therefore it is initially p-type semiconductor. It is initially p-type semiconductor. After that I am going to calculating amount of Na initially. That means number of impurity atoms present in this semiconductor. So you concluded finally it is a p-type semiconductor. Now I am going to calculating how many number of Na present in that. So from this you can write Na is Nd minus N naught. Okay, so Nd minus N naught is 4.4 into 10 power 16 minus 2 into 10 power 16. Now it became 2.4 into 10 power 16 per centimeter cube. So initially it is a p-type semiconductor with amount of doping, with amount of impurity they added. Na equals to 2.4 into 10 power 16 per centimeter cube. That is the Na. Now at this, so now this is P and its Na value we got, it is 2.4 into 10 power 16 per centimeter cube. Okay, So now once I know the value of this, I go and calculate its resistivity at initial condition, at initially. Therefore, its resistivity rho naught is 1 by sigma naught, which is 1 by under steady state whole concentration into P naught into Q into mu P. But P naught is nothing but a approximately amount of doping what it has, Na. Just I am substituting the values. 1 by P naught is Na. It is 2.4 into 10 power 16 into Q. 1.6 into 10 power minus 19 coulomb into MP. See, they given mu n equals to 2 times mu p equals to 3000. From that mu p is 1500. 3000 by 2. 1500. 1500. Now simplify this. So 16, 17, 18. Now it is 10 power minus 1. So you can write it as 1.5. Okay. Now 1 by 2.5 into 1.6 into 1.5. 1.5 you can write 3 by 2. So it is 0.8. Okay. 0.8. Now 1 by 2.8 into 0.8 into 3. So that is your answer. Now 1 divided by 2.8, 0.8, just a minute, 2.8 divided by 0.8 divided by 3. Yes, it is 0.148. 0.148. Okay, ohm to centimeter, because it is a resistivity. That is the resistivity of that semiconductor. See this problem. Initially they given see this. Initially they given a semiconductor with some resistivity. They did not given that value. It's initial resistivity they mention only. That's it. After that, the material is remelted. Your semiconductor is remelted and doped. Remelted in the sense heated and doped with 4.4 into 10 power 16 arsenic atoms per centimeter cube. And after remelting and doping, it became a new type semiconductor, new crystal. And its new crystal resistivity they given 1.1 ohm to centimeter. And they mention at the same time the new crystal behaves like n-type semiconductor. Now you need to identify initially it is which type of semiconductor initially it is, and the concentration of impurity atoms. Initially it is some type of semiconductor, it may be n-type or p-type, whatever it is. Now at that initial condition, what is the concentration of impurities present in that, or impurity atoms present in that, and at that time it's a resistivity. These three things you need to calculate. Just one clear point I know only from this problem, from first line to last line, is new crystal, its resistivity, and it is n-type. Just I am applying that. After applying that, I calculate the n0 value. Now after that, this is the main point, sir. Here you need to take a decision. After that, observing after n-type semiconductor, its electrons is n, it is less than the amount of doping what you done. Okay, see, if it is a intrinsic semiconductor, number of electrons is equals to or more than amount of doping. Okay, so it is not an intrinsic semiconductor. Why? Because number of electrons is less than the amount of doping. Okay, fine, leave it. If it is a n-type semiconductor, sorry, in intrinsic, Ni after doping of Nd, electron concentration is more than doping or equal to doping. So, but that is not the case here. Doping is more than number of electrons present in that. Okay, that means after doping with Nd, number of electron concentration is decreasing. See, this is intrinsic. Right? After doping, if it is N type, electron concentration increases. If it is P type, electron concentration decreases. So after doping, electron concentration is decreased. That's why it is a p-type semiconductor. It is a p-type semiconductor. Okay. So initially it is a p-type semiconductor and you are adding Nd to that. After adding Nd to that, you are converting that material into a N-type semiconductor. Initially it is a p-type semiconductor. After adding some compensation doping Nd, you are converting that one into a N-type semiconductor. At that time, the net electron concentration equals to Nd minus Na. That's what I applied. And after that, I know the value of N0 already calculated, and Nd also we know that because they given that one. By substituting those two in that, I got the Na value. That means initial semiconductor impurity atom concentration. So once you concluded it is a p-type semiconductor and initially amount of impurity in that, then immediately you can calculate its resistivity. That is the thing here I done. So the important point here is in this problem, this one, estimating this one from these two values of Nd and N0, what you get. Okay, you need to get a conclusion. Which type of material it is, what happened in that material. That is the very, very important point in this. Okay, conventional problems on semiconductors, and in not only this one, in every subtopic and every subject, conventional problems, giving where data, substituting in an equation, getting the answer. Simple substitutions. Such type of problems are not giving nowadays in competitive exams. Okay, so some concept you need to apply in that. Okay, so they are giving problems like this. Okay, please concentrate on these problems. Next problem is, see, a gallium arsenide sample is doped that the electron and hole components of currents, are equal in an applied electric field. Say this, electron current and hole current components are equal. If you take a current component, we have two types of current components: drift current component and diffusion current component for electrons as well as holes. For electrons, we have drift current component and diffusion current component. Similarly, for hole, we have a drift current component and diffusion current component. Okay, now these two current components are equal, but here they given one point. In an applied electric field, they mention, once it is applied electric field, the current component is I drift only, drift current component only. Okay, that means J drift by electron, J drift electron equals to J drift hole. So that is the statement they given. Calculate the equilibrium electron hole concentrations. Under equilibrium, what is the electron concentration and what is the hole concentration? You need to calculate that. What is the electron concentration and what is the hole concentration? You need to calculate that. Okay, and they given the net doping, hole concentrations, the net doping and sample resistivity at 300 Kelvin. Net doping also you need to calculate and resistivity also you need to calculate. Okay, see, sample is doped, clearly they mention it as a doped. that the electron and hole components are equal. That means it is doping simultaneously with Na and Nd. So that means here you get Na and Nd. So whatever the value of N naught you get, that is nothing but approximately Nd. So whatever the P naught you get, that is approximately Nv. So net doping is either Na minus Nd or Nd minus Na, and we get resistivity from that. Now I am going to equating their current components. So J drift by N is N naught into Q into mu N into applied electric field. So J drift by P, P naught into Q into mu N into applied electric field E. So here, see, because they mentioned is applied electric field. Both the case they are applying a single germanium. They are applying electric field, same electric field for electrons and holes. E cancel, Q gets cancelled. From this I got N naught equals to P naught into mu N by mu P. Already they given mu N and mu P values to you, 8500 and 400. Just substitute P naught into mu N 8500 by 400, that is 85 by 4. It is 21.25 into P naught, that is N naught value, and they given Ni value also. So we have mass action law. From mass action law, one can write N naught into P naught equals to Ni square. Already you know the N naught value, 21.25 into P naught. Just substitute that. Into P naught equals to Ni square. Therefore, it is became P naught square. So now we can write P naught equals to Ni by square root of 21.25. Now Ni they given 1.79 into 10 power 6 by square root of 21.25, that is 4.6. Now it is 0.389 into 10 power 6 per centimeter cube. So therefore P naught is 0.389 into 10 power 6 per centimeter cube. Now from this get the N naught value, and therefore N naught is 21.25 times P naught. 0.389 into 10 power 6 per centimeter cube. Therefore N naught is into 21.25. It is 8.26. 8.26 into 10 power 6 per centimeter cube. See, this is a 10 power 6 P naught. N naught is also 10 power 6. Okay, not much variation. So now therefore Na is approximately P naught, that is 3.89. so I can take it as a 3.9 approximately. 3.9 into 10 power 5 per centimeter cube, and here also Nd is approximately N naught, that is 82.6 into 10 power 5 per centimeter cube. So this is the first one you have to calculate. Next one is net doping. So net doping is Nd minus Na. Nd minus Na. It is Nd is 82.6 into 10 power 5 minus 3.9 into 10 power 5. So that is 78.7 into 10 power 5 per centimeter cube. So this is the net doping. And they asked one more thing to you, that is resistivity of that sample. So once you know the P naught and N naught, its resistivity is rho, which is 1 by sigma, equals to 1 by Q into N naught into mu N plus P naught into mu P. Okay, just substitute values. Therefore rho equals to 1 by Q, 1.6 into 10 power minus 19 into, okay, N naught value. So just before we got N naught, it is a 82.6 into 10 power 6 into mu N. So we need mu N value. So mu N is 8500 into 8500 plus P naught. P naught value 3.9 into 10 power 6 into mu P. Mu P they given it as 400. So you need to simplify this. Just a minute, I will check the mu P value. Yeah, 400. Now I am simplifying this. Therefore rho equals to, so I am taking 10 power 6 common, and these two zeros also, now it became 10 power 8. So it is 10 power minus 11. Now it became 10 power 11. Okay. Now, so denominator is 82.6 into 85. That is, this is 10 power 11 by 1.6 into, this part is 7021 plus 3.9 into 4, approximately 15.6. Now 6 plus 7021 plus 15.6 equals to this much into 1.6. It is a 36.5. So 10 power 11 by, just a minute, all I think so, it is a 7021 plus 15.6. Yes, 15.6 into 1.6. So this is a 11258.56. So now it is 1 divided by 11258 0.56. So it is 8.5 in 8.8 into 10 power minus 5. 8.88 into 10 power minus 5 into 10 power 11. So its resistivity is finally rho is 8 point approximately 9 into 10 power 6 ohm to centimeter. That is the resistivity of that. Okay. So 6 plus 8 minus 11, 10 power 11. Okay. So this is the resistivity. So I'm moving to next problem. See, in the figure, ln of rho I is plotted as a function of 1 by t. See, ln of rho I is intrinsic resistivity, is a function of temperature. That means your temperature is not a constant. That is the meaning of this. Where rho I is the intrinsic resistivity of silicon, T is the temperature, and the plot is almost linear. So this plot is almost linear. That is the point given to you. That means it is varying linearly with respect to this. Okay, linear. The slope of that line can be used to estimate. What is the slope of this? They are asking simply. By using that slope, which parameter you can calculate? Okay, now so to get the slope, first of all, I am going to getting the ln of rho I value. So we know rho I value. Rho I is nothing but a 1 by sigma I, and its value is 1 by Ni into Q into mu n plus mu p. Mu n plus mu p. Okay. Now, and at the same time we know the Ni value. We know Ni. So Ni is some constant A into T power 3 by 2 into E power minus Eg by 2 kT. So to solve this problem, first you should know all this. Now take this Ni substituting here. Therefore, rho I is 1 by Ni, that means A into T power 3 by 2 into E power minus Eg by 2 kT into Q into mu n plus mu p. Now, just 1 minute we concentrate on mu n and mu p. Already we studied mobility is a function of temperature. That means mobility is changing with respect to temperature. Okay. For a low temperatures, due to impurity atoms scattering, mobility is changing. At high temperatures, due to silicon atoms, what we have, due to that atoms scattering, mobility is changing. But at high temperature, scattering of atoms, that means silicon atoms, they are very high in number. Because of that, mobility is going to be decreasing due to decrease in the mean free time. That means average distance between the average time between the two successive collisions, that is the mean free time, that is decreasing because of more collision, high number of collisions. So scattering mechanism, more number of silicon atoms is there at high temperature, though they are going to be vibrating. Anyway, mobility is varying with respect to temperature. Okay, now here which one you need to take? See, generally operating condition is room temperature. Okay, room temperature, and here they are saying it is linear. Okay, just I am taking little bit just away from the room temperature. At that case, I can write whatever the electron mobility we have is directly proportional to T power minus 3 by 2. T power minus 3 by 2. Okay, sir. Now it is some proportionality constant mu n naught under steady state conditions mobility into, or some proportionality constant into T power minus 3 by 2. Similarly, I am writing mu p also as mu n naught into T power minus 3 by 2. Okay, now just take that values, substitute in mu n plus mu p. Now we can write mu n plus mu p is, by substituting these values into this, T power minus 3 by 2 into mu n naught plus mu p naught. Now in place of mu n plus mu p, I am writing this one in this. Therefore rho I is 1 by a into T power 3 by 2 into e power minus eg by 2 kt into q into T power, this value, this one, T power minus 3 by 2 into mu n naught plus mu p naught. Okay, now this T power 3 by 2, T power minus 3 by 2 gets cancelled. And one more thing, this A is a constant and Q also a constant, and these two are also a constants. Now I am taking let, I am representing that one by a constant C. C is a constant, and which is equals to 1 by A into Q into mu n plus mu p, mu n plus mu p. So now we can write 1 by sigma I is, so this total thing I am representing by a constant C by this one, e power minus eg by 2 kt. Now it became e power eg by 2 kt. 2 kt. Okay, but problem they given ln of rho I. Now I am taking natural log on both sides. Now it became ln of rho I is ln of a plus a into b. So it is ln of a plus ln of b. Ln of some constant plus ln of this one. Ln of e power eg by 2 kt, which is ln of sigma I equals to. Now first I am writing this one and this one gets cancelled. It became eg by 2 kt plus ln of c. Now it is on y-axis. So the plot they given is, this is the plot they given. It is ln of sigma I and it is 1 by t. On y-axis they given ln of rho I, so it is y. Okay, and 1 by t is there here. Now this 1 by t plus c. Okay, this is some constant. Ln of c is the some constant. Okay, now it is eg by 2k. Okay, eg by 2k. So it seems to be y is equals to mx plus c. The equation seems to be. This is the equation for a straight line. Linearity is nothing but a straight line. Okay, linearity means for every input there should be a corresponding output. One-to-one mapping is nothing but a linearity. Now m is nothing but a slope. Now that slope of that line m is Eg by 2k. Slope m is Eg by 2k. So k is a constant, Boltzmann constant. Okay, now by using the slope you can measure, or one can measure its energy gap. So just go back to this. Now here is your energy gap. Option A is the correct one for that. Okay, is it okay, sir? So like that you have to solve the problems on this. See here, there no numerical, nothing they given, simply they given a statements and a plot. Okay, from that statement we follow the procedure. Next problem. The figure below shows the doping distribution in p-type semiconductor in log scale. This is the log scale, sir. They clearly mention it is log scale. It is 1 micrometer and it is 2 micrometer. So let us, I am taking this is x1 and it is x2. If it is x2, that means log of x1 equals to 1 micrometer. So one in log we have a base 10 and log of x2 base 10 equals to 2 micrometer. That is the data they given from the plot. Later we simplify that, whatever we want. Next, the magnitude of electric field in the semiconductor due to non-uniform doping in kilovolt per centimeter. Yeah, see, your semiconductor is not uniformly doped. Okay, it is not uniformly doped. Okay, so because see at x1 its impurity is 10 power 14 and at x2 its impurity is doping is 10 power 16. Okay, there is a change. It is not uniformly doped. At one side it is 10 power 14, on the other side it is 10 power 16. How to solve this type of problems? See this. Now first I want to get the amount of electric field. There is a standard equation I want to derive for this. Okay, anyway, your semiconductor is not uniformly doped, fine. At the same time, there is no electric field applied externally. Okay, because of that, the net current passing through this one is 0. Once current is 0, in this sense, its current density due to electrons is 0, current density due to holes also 0, equal to 0. Now I am going to using that point. Here, no bias is applied, bias voltage is applied to semiconductor bar. Therefore, its Jp equals to 0. Jp means J drift plus J diffusion. J drift plus J diffusion. Now write the equations for drift and diffusion. Okay, now drift current density is P into or P naught into Q into mu P into electric field plus diffusion, sorry, drift value. Okay, diffusion is minus dp into q into mu q into dp by dx, that is the value. Here NA is varying with respect to distance. Let us take this one is x. Now this is the plot of NA of x. This NA of x is nothing but a whole concentration. Okay, now this is not P naught. Under steady state it is not it is not constant, it is changing. That's why I am changing it as only P, not steady state value I am taking. So from this, now I am equating both, taking this one this side. Now P to, so P into Q into mu P into E equals to dp into q into dp by dx. Now q gets cancelled, therefore electric field E equals to dp by mu p into 1 by p into dp by dx. You may ask one thing, sir, the way how they doped in that, okay, and how can you relate the, how if it is not uniformly doped, how electric field is forming in that? Okay, that means if it is uniformly doped there is no electric field. Yes, if it is uniformly doped there is no electric field. See this, if it is uniformly doped there is no concentration gradient in that, there is no dp by dx. So once dp by dx is 0 in this equation, now electric field became 0, there is no electric field in that. So because of this non-uniform doping, internally electric field is going to be developed. Okay, now the equation for this electric field is, therefore E is dp by mu p is vt into 1 by p. So I am taking it as 1 by p is nothing but a NA of x into dNA of x by dx. Now you know every value, just substitute. So at room temperature Vt is 25 millivolts. Okay, and dN of x by dx. So here take this. Now two values of Na. This is the first one and this is the second one. Dn is this one minus this one is a dn, and this is the dx. This is the dn of x, Na of x. So you get this value from that plot, and Vt we know that it is 25 millivolts. Okay, now Na of x, what is the value of Na of x? That is the point. Here Na of x is having two values, 10 power 14 and 10 power 16. Okay, if you want to take an average value, that is the midpoint of that, at a specified value of x, that is, but it should be a varying, it is a function of x. So that is the problem here. Now which value of Na we need to take, either first value or second value, which one we need to take? Now I am doing a little bit modification in this equation. See, so our expression is E equals to Vt into 1 by Na of x into dNA of x by dx. Okay, so there if we have a ln of x, we are writing this 1 by x into dx by dx. For example, it is ln of y 1 by y into dy by dx. Okay. So in place of this, we can write ln of this parameter y. This is just differentiation of this d by dx. So d by dx of ln of y is nothing but a 1 by y into dy by dx. Now in place of y here we have na. Now this portion of the equation I am writing as Vt, that one initially, into d by dt or dx of ln of na of x. That's it. Now your final equation is E is equals to, therefore electric field E equals to Vt into d ln of x, ln of na of x by dx. So now you can take it as Vt into d ln of x, means ln of na of x, that is na of 2, ln of na of 2, ln of na2 minus ln of na1 by x2 minus x1. That's it. Okay, now we need the values of this. So which is Vt into ln of na2, they given 10 power 16, ln of 10 power 16 minus ln of 10 power 14 by x2 minus x1 we need to get. First I am simplifying this, that became Vt into ln of 10 is a 2.3 into 16 minus 14 is 2 by x2 minus x1 here. Now I am getting x2 and x1 and x2 value. See, x1 and x2 is not equals to not 1 micro and 2 micro. Clearly they mentioned here, they given it is in log scale. In a log scale they given. Doping distribution in p-type semiconductor in log scale. This is log scale. So now the expression is log x1 base 10 is 1 micrometer. From that you need to get the first x1 value. So from this, x1 is how much? 10 power 1 micrometer, x1 value. So in terms of centimeters, it is a 10 power minus 3 centimeters. Similarly, it is x2 is 10 square micrometer, that is 10 power minus, it is 10 power minus 4, now it is 10 power minus 2 centimeter. Okay, so we can write this is 0.001 and it is 0.01. So these are the values of x1 and x2. So x2 is 0.01 and x1 is 0.001. Now just do this, simplify that. 0.01 minus 0.001, that is 9 into 10 power minus 3. So 9 into 10 power minus 3. Okay, so now substitute it. Vt 0.025 or 25 milli, you can take it, no problem, because here is available, that value is available in milli. 10 power minus 3, it is going to be cancelled. 25 milli 10 power minus 3 into 2.3 into 2 by 9 into 10 power minus 3. That is the electric field. Now just simplify that. So this one and this one gets cancelled. Okay, now 25 into 250, 50 into 2.3, 50 into 2.3, that is 115 by 9 divided by 9. So by 9, it is a 12.777 volt per centimeter. Okay, so this is the electric field. So in problem they ask kilovolt per centimeter, so which is 0.0127 kilovolt per centimeter. 0.0127 kilovolt per centimeter. Okay, so that is the value. Now just a minute. So okay, ln of 10 power 14, 10 power 16. It's okay. So 14 minus ln of, fine, Vt into ln of 10 is 2.3. ln of 10, yeah, 2.3 common. So 16 minus 14, 2. Vt 25 milli. Okay, 0.01 minus 0.001. Okay, 25 into 2.3 into 2 milli, 10 power minus 3 by 9 into 10 power 3. Cancel. 25 into 250, 50 into 2.3, 115 by 9. So 12.777 volt per centimeter. Yeah. 0.0127 kilovolt per centimeter. Yeah. So this is the value. Okay, sir. So like this, you have to solve the problems. Now I am moving to next problem. So see, an intrinsic germanium wafer is doped with a shallow acceptor density of that means they given Na, acceptor density of 3 Ni by 2, where Ni is the intrinsic carrier concentration. The temperature T, at temperature T, all the acceptors are ionized. It means whatever the impurity atoms you added to that, all the impurity atoms are useful for providing a charge carrier. That means all are replace the silicon atoms. That means all are useful. Now calculate the hole density. So hole concentration you want. Simply they are saying, so far we solved some problems. The amount of Na is this much, Nd is this much. What is the electron concentration and hole concentration? This one also similar to that, but the only difference is they given the value in terms of Ni. Only that is the difference. Now if you observe this is greater than Ni, but not that much. So you need to go for a proper standard equation, exact equation. Now the hole concentration is Na by 2 plus square root of Na by 2 whole square plus Ni square plus Ni square. Now it is Na by 2. So just I am substituting the value. Na is 3 Ni by 2 plus square root of 3ni by 2 into 2 whole square plus ni square. Just simplify this. It is a 3ni by 4 plus 3ni square. 3 square is 9. 9ni square by 16. Square root of 9ni square by 16 plus ni square. Now take LCM, it became 16. 16 plus 9, 25. That is 5ni square. 5ni by 4. So 3ni by 4 plus 5ni by 4. So that is 8ni by 4. So that is 2ni. That is the value of ni what we have. Okay, sir. So like this, you have to solve the problems. Okay. Now I'm moving to next one. See, an n-type silicon bar of 0.1 centimeter long, that means that the length or long is 0.1 centimeter, and 100 micrometer by 100 micrometer cross sectional area. So area is 100 micrometer by 100 micrometer. Next, the majority carrier concentration of 5 into 10 power 20 per meter cube. So it is n type. So majority means it is n naught. Under steady state electron concentration is 5 into 10 power 20 per meter cube. And the carrier mobility is 0.13 meter square per volt to second. So it is mu n 0.13 meter square per volt to second at 300 Kelvin. If the charge of the electron Q is 1.6 into 10 power minus 19 coulomb, then the resistance of the bar is, so they want the resistance. See, we know the value equation for resistance. Resistance R is equals to rho L by A, and rho is nothing but a 1 by conductivity. So L by conductivity into A. This is n type, so it is L by conductivity is n naught into Q into mu n into A. So all parameters in terms of meters but except L. Now it is 0.1 into 10 power minus 2 meters. So it is 10 power minus 3 meters. Now it is 100 into 100, 10 power 4 into 10 power minus 6, 10 power minus 6, 10 power minus 12, which is 10 power minus 8 here meter square. Substitute the values. Therefore, R is L value 10 power minus 3 by n naught 5 into 10 power 20 into Q 1.6 into 10 power minus 19 into mu n 0.13 into area 10 power minus 8. That's it. Now just simplify this. It is a 10 power minus 19 and it is 10 power 20. Now we can write this is 16. So now it is 10 power minus 3, it is 10 power 8, so it is a 10 power 5. So 10 power 5 by 5 into 16 into 0.13. So it is, now R is, so 100 into 10 power 3 I am writing by 5 into 16 into 0.13. In this 20 times 4, 5, 4, 4. Okay, simplifying. 5 divided by 4 divided by 0.13. It is 9.6 into 10 power 3 ohms. So it is approximately 9.6 kilo ohms. Okay, in resistance point of view, you can take it approximately it as a 10 kilo ohms also. It's not an issue. Okay, now we check the options. Yeah, 10 power 6 ohms, 10 power 4 ohms, 10 power minus 1 ohm, 10 power minus 4 ohm. See, we get 9.6 kilo ohm. So approximately it is 10 kilo ohm. So which is 10 power 4 ohms. This is the option. Option is the B for that. Okay. Okay. So my dear students, like this you have to solve the problems. Sometimes you get direct substitution from problems, but rare conditions. Remaining times you have to apply the concept. Whatever the concept you learn, you have to apply that concept. And sometimes for 2 marks, they will mix the multiple concepts and they will design a problem. Okay, so to solve that problem you should be thorough with all the concepts. Okay, and now thanks to one and all for spending your valuable time with me. So next session we solve more number of problems. Next session we go to more number of problems. Okay, so just a minute. And don't forget to use my code VRAO10 during subscription. By using this code you get 10% discount. Okay, and hit on this bell button to get the notifications and join our Telegram group to get the updates of our upcoming videos. Okay, and don't forget to subscribe this and please give your valuable comments on YouTube, so to strengthen ourselves and to provide a quality and best information to the upcoming students. Okay, thank you very much. Thanks for spending your valuable time. So once again I am welcoming you all to Unacademy. Thank you.